So the hexadecimal numbers, if it's a hexadecimal number, I use this notation. Okay, 3. What was it? 3. 0. It starts with 0. Yes, 0, 3, 4, 5. So this 0 in binary means 0, 0, 0, 0. This 3 in binary means 0, 0, 1, 1. This 4 in binary means 0, 1, 0, 0. And this 5 in binary means 0, 1, 0, 1. Actually, this is a 16-bit number like this. Okay, so in the figure, if you remember, these were connected, guys. These were connected. Let me share it first. So guys, the first two zeros, these guys, are connected. These guys, the first two zeros, these guys are connected to here, guys. So if I stop sharing, they are these guys. When I say connected, they are connected like cables connected there. So if at those 2 bits there are zeros, they are automatically connected to the arithmetic logic unit. Okay? And let me just share my screen again. These bits are connected to here. This 3 is connected to here. This 4 is connected to here. And this 6 is connected to here. So what happens, guys? What happens is, it's 0, 0. So if it is 0, 0, you'll remember that the operation will be summation. Okay? So it is 3 here, which means this address 3 is selected. So if address 3 is selected here, the data that is coming out of here will be the value inside address 3. So if you connect 3 here, you will have the value which is written in address 3. So as you can see, it was 7 written in address 3. So if this is 4, the data will be the data inside address 4. And the ALU will calculate the summation of them. What is the summation of 7 to 5? It is 12. And 12 is, in hexadecimals, is C. It is connected to the destination data register. It's connected to here. And 6 is connected to here. So the registers is designed such that 6 will be written automatically to the data. So that's how you calculated the summation, guys. This is called an architectural design. By using this architecture, that's why we designed this architecture this way. That's how we did the calculations. That's why, since you had this value here, it calculated this. I get to the next clock. The clock continues. So it was here, as you can see. The next clock is this. So automatically, when the clock continues, the program counter will be 1. So when the program counter becomes 1, the next value to be fed will be here, this one. So let me do it. So it is here. So as you can see, this slide is showing still the first line. So it was here. So do you remember the things that I've written on the screen? So this is because of these zeros. It's an add operation. I've added these. And the instruction is called an opcode, operation code. We've done the operation. Next time. So it was 1. So, and finally, at address 6, I have written C. Okay, next line. It became 1, and it became this value. So when this became, I had this value, things changed. All the bit connections changed. Since this is 1, it's going to be 1. It's connected to here. Because this bit is connected to the least significant bit. Let me show you. So as you can see, let me just write it on the screen. I'm going to stop sharing for a moment. I'm going to write it on the screen. So guys, so the next operation is 1, 3, 4, 7. So since this is 1, this is 0, 0, 0, 1. I'm going to correct it, guys. These are not connected, but these are connected. I'm sorry. So these are connected to S1 and S0. And this is 0, 0, 1, 1. This is 0, 0, 0, 1, 0, 0. And this is 0, 1, 1, 1. Can you see it? Yes, this is 0. So they are connected. So what it's going to do, let me share my screen again. Okay, yes, screen is shared. So 3 is connected, 4 is connected. I'll get the values inside 3 and 5 here, 7 and 5, 7 and 5. This is 0, 1. So 0, 1 will make subtraction because that's the data sheet of it. It will subtract 7 from 5, 5 from 7. It's 2. It's connected to the destination register. I've written 7 here. So into address 7, 2 will be written. That's how microprocessors work, guys. So this is the third one. Just study this yourself. You can do this. Okay, there's another example. Just I recommend you to do it on at home. We are going to do it next week, but do it at home so you all understand it. What type of operations do. So this is the idea, guys. This is how microprocessors work. Okay, I guess this is all I'm going to be talking about this week. I'm ready to get your questions now.
Hocam ben şey soracaktım. Alanın içindekileri biz kendimiz mi karar veriyoruz yoksa sürekli hep böyle mi? Yani 0 geldiğinde hep toplayacak mı? 0 geldiğinde hep çıkartacak mı? O değişiyor mu yoksa hep aynı mı?
Very good question. Your friend is asking who put the values inside the instruction memory? Who decided that 0, 1 means subtraction, 0, 0 means addition? I'll answer them separately. First, who will put these values inside? Well, you will have other interfaces to write into the memory. Or, I mean, in normal computers, you can write into the memory whatever you want. So there will be other interfaces allowing you to write in them. This is a very simple microprocessor design. That's why you couldn't write. But believe me, there are microprocessors like this in your washing machine. Do you ever program your washing machine? No, it comes from the factory, all programmed. And in your washing machine, it does some sequential operations, right? First, get the water, then pump the water, then just turn the wheel, kind of. They have an instruction set like this coming out of the factory, nobody can change. So both are true for memory. And about your question, who decides 0, 0 is addition, 0, 1 is subtraction? Guys, that's called the microprocessor architectural design. The guy who designed the microprocessor decided this. We are going to use an ARM company M4 microprocessor. We are going to learn the design. We are not going to design the architecture. Designing the architecture is the course computer architectures. Learning the design of a microprocessor is the course microprocessors, our course. Okay?
Tamam hocam.